Welcome. My name is Marcel, and I'm presenting Cafca, high-quality novel view synthesis of expressive faces from casual few-shot captures. Let's dive right in. Our goal is to enable high-quality novel views from sparse casual in the wild captures. So we take images with a smartphone or a DSLR camera, and from only 3 images, we reconstruct high-quality novel views with details on the eyelashes, on the skin, and more. Today, I would like to convince you that to do this, a prior trained on purely synthetic data is actually sufficient. This prior can generalize to out-of-distribution inputs like real photographs or even stylized faces. Now let's see how this works. Our pipeline consists of 2 steps. The first step is a pre-training step. We train a prior model on purely synthetic data. In this step, the model never sees any real photograph. In the second step, we perform a per-scene fine-tuning. This means we capture 3 images of the target subject and then we fine-tune the model. Now let's see how we pre-train our prior model. The first step is to generate a large synthetic dataset with 1,500 identities, 13 expressions, and 30 views each. These renderings are generated with a Blender pipeline and traditional CG assets for clothing, hair, and so on. We render all faces in the same environment in different configurations. What we find is that for this dataset, size matters and also diversity in terms of geometry. So we need to put in as many assets and different facial shapes as possible. What is not important at all is diversity in terms of appearance or lighting. Now, given this dataset, we can optimize our prior model. And our prior model is implemented as a conditional neural radiance field with a MIPNERV 360 backbone. The modification we make to MIPNERV 360 is that we condition it on the 3D morphable model parameters for identity, beta, and expression psi. So the NeRF rendering equation changes to this conditional formulation. In addition, we inject additional information from a latent code W. The latent code W represents all the out of 3DMM characteristics like clothing and appearance. This model can then be optimized with standard MIPNERV 360 losses for reconstruction, an L1 loss, and the proposal loss, which is specific to the MIPNERV 360 architecture. This model is optimized as an autodecoder where we have n latent codes, 1 for each identity. Now let's see the results. What did the prior model actually learn? In the first column, we interpolate the latent code for identity, beta. As you can see, the facial expression remains constant while the facial shape changes. In the second column, we interpolate expressions. In the third column, we interpolate the latent code W, which is responsible for clothing, hairstyle, and so on. Of course, we can also interpolate different latents at the same time. So in the last column, we jointly interpolate expression and latent. So this model is already quite interesting to see what it has learned, but we want to use it to fine-tune it to sparse inputs and to get high-quality reconstructions of real subjects. And this step, again, contains 2 sub-steps. First, we need to obtain the parameters for the 3D morphable face model and for the cameras. So given 3 images, usually captured with a DSLR camera or a smartphone, we fit the 3D morphable face model by first estimating key points and minimizing this energy function. The last step is to fine-tune all model parameters. Here, we first warm up the model by only inverting to the latent code W, and then fine-tuning all the model parameters theta. The objective function for this fine-tuning incorporates the same losses as when training the prior model, and in addition we add 4 regularizers, one on the normals, one on the view directions, and one on the distortion. And this is the full pipeline. Now, one thing I haven't mentioned is that when you capture people in the wild, it is actually very, very hard to keep still. So if you have ever captured a human with a smartphone, or even did a selfie capture of yourself, then you notice that you do micro motions, and these micro motions lead to a lot of errors down the line. And if you want to reconstruct details like individual hair, eyelashes, or skin pores, then this will not lead to good results. So how do we handle this during inference time? If you pay close attention to the 3DMM fitting step, then you can see that we fit 1 identity coefficient, beta, but 3 expression coefficients, psi. And this allows the model to differentiate between different expressions that happen during the capture. So what we do is we fit per frame expression codes, psi, and then we perform a weighted interpolation during rendering. So if you look at it at the face from the left side, you will mostly use the expression code from that side, and as you smoothly transition to the right side of the face, you will interpolate the different codes fitted based on the distance of the camera. And while this solution is very simplistic, we found it to be crucial to enable truly casual captures with just simple smartphone or DSLR cameras. Now let's look at some results. We evaluate our method on the multi-face dataset because it provides high quality and high resolution multi-view images. And we do this both quantitatively and qualitatively. But we want to show the applicability of our method to truly in-the-wild captures. So here are some examples where we capture 2 people in the garage and outdoor with a DSLR camera. The third column shows smartphone captures. On the top right, we even have a selfie capture. The last column shows what happens when we push our model to the very extreme. On the top right, we have a smartphone image where we invert just a single photo. In the second row, we download an image from the Rodin website. And for the bottom 2 examples, we take stylized faces, a child, and a painted face from the LP3D paper. Now let me give some examples about generalization. Our synthetic dataset doesn't contain any tongue out samples. So it contains tongues inside the mouth, but it never leaves the mouth. Still, for this example, our model was able to reconstruct a valid tongue that is outside of the mouth. In the second example here, we reconstruct children and the stylized face from just a single input image. And our synthetic training set again doesn't contain any children or stylized faces, and it also doesn't contain any face paint. We also report detailed ablations on dataset size, training time, and synthetic data quality. Here is the summary. We find that the dataset size, in terms of the number of identities, is crucial. The more identities we render, the more diversity we have in terms of geometric shape, the better the results. What we find to be nearly completely irrelevant is diversity in terms of textures, environments, and lighting. And we also don't find a difference when training with real data or only synthetic or mixed. Let me make one example about the diversity of textures. When we push this to the extreme, we can pre-train a prior on only grayscale images. Then the only RGB images we feed are the ones used for fine-tuning. Now look at the results. It looks nearly as good as the result when training on a prior with RGB images. Now before I close, let me give you one sneak peek about a potential future work. We can apply our model out of the box to captures of multiple images. So here we capture a smartphone, a face with 12 different images of various expressions and different viewpoints. And we just run our model out of the box. And then we render the reconstructed avatar with training set expressions. As you can see, there are detailed reconstructions like wrinkles on the skin. And while this result is not perfect yet, I think it's a promising avenue for future work. Of course, our model is not perfect. So when you look closely at these examples, on the left you can see that the glasses are sometimes painted on top of the skin. This could potentially be mitigated by rendering more glasses in synthetic training data. On the right side, we have a very complex mouth interior region, and upon novel view synthesis, this region has some view-dependent effects that are unrealistic. So to close, for the task of high-quality novel view synthesis at high resolutions, a prior trained on purely synthetic data is sufficient. It can generalize to real inputs. We hope to see this idea leveraging synthetic data for pre-training. We hope to see this in future works for facial avatars and more. Our large synthetic dataset with over 1.7 million face images is available for academic research. Download it now. Thank you very much for listening. Thank you.